slide this table a little bit that way.
Yeah, hold on. Let me, How are you doing, Neal?
Good. I was just talking to Ruben. I'm coming out of the black hole of a second child.
Yeah.
But, how about yourself?
Well, except for this back, I tweaked my back, and as a result, I'm sort of suffering a little bit. I've been giving these lectures sitting down.
Oh. Oh, no.
But as a result of this, I got an incredibly nice parking spot.
That is silver lining
It's
to
over.
the extreme.
Yeah.
I was wondering why this was an awkward place for
Yeah, so, I mean, you can certainly do supersymmetric theories.
Neal,
and
some
high
mic here for you.
I know
It's already turned on. The video will start recording. Okay. I will stop saying embarrassing things.
But I think the answer... So I think in the end, the answer is I don't think you can do what you're thinking of doing. To get the Fermions in that way, I think really requires anti-commuting force.
Okay. I'll introduce myself.
It's said very often that superspace is new dimensions, because anti-commuting.
Yes. So you're saying if I do something like that, it has to be supersymmetric.
It has to be.
It is supersymmetric.
Yeah, I think so.
I was thinking. Okay, sit down.
Huh? Dark matter theory.
Well,
No. You should. I assume you know everything that I will say. Oh, sorry you feel bad. I'll see you later.
Well, I'll try to join the guys for lunch.
Yeah.
Eat lunch in the...
Yeah. Assuming they let me in.
You need to get these cards.
Yeah, I think I have them. All right. So I guess we will start. So I'm Neal Weiner. I'm talking to you about dark matter theory. That is what I've been assigned to talk to you about. So dark matter theory is a interesting topic to lecture about because, of course, we don't know what dark matter is. So it's not like jets or collider physics where there's some sort of well-defined theory and you proceed to explain its phenomenology in specific ways. Really, it's a hodgepodge of ideas that come from different sources. And so the goal of these lectures is to try to put it into some coherent framework. Now, I will tell you at the outset that there is no coherent framework. All right? And that is because the ideas for dark matter come from a lot of different sources. They're motivated by a lot of different things. And so that will just be how that is. And my goal is to provide you with some phenomenology and examples of models and things like that that I think are relevant. Now, because dark matter is such a diverse subject, different people have different perspectives on dark matter and what makes things important. I have my perspective. Other people have their perspectives. So this is just a caveat that you should take everything that I'm saying as a specific perspective of a specific person, and that you would be well served to go out and talk to other people and get their perspectives as well. Fortunately, there are 4 other lecturers on topics related to dark matter, and so no matter what I do, it is unlikely I can pollute your minds too much. But I will try. So let me begin. Before we talk about dark matter, I need to give you a cheat sheet for cosmology. I have some notes. I'm sort of writing them digitally, and these will be presumably put up on the website. And I will just encourage you to update them as we go, because I will be updating them as I go. So the thing that might be on the web today won't be the thing that's on the web tomorrow. So let's begin with a cheat sheet for cosmology. Now, this board height is a little odd. It was designed for somebody who's a little bit shorter than me. Is this, how far down is like good? To like here? A little lower? Down to about here? That's about good? Okay. Well, except for I can't raise this one. Well, I guess I can, but then things get covered up, and I don't want people to have things covered up. So, okay, so let's begin. I know you'll have lectures on cosmology that will give you great detail about how the expanding universe works, but there are a few essential elements that are important for you to know for discussion of dark matter. And I'm going to try and boil those down to the basic ones so that we can work with them. And you'll forgive me to the extent that this is slightly redundant, but I think at this point, given what you've heard so far, this shouldn't be too redundant. So in an expanded universe, we characterize the universe by some scale factor A of t. So that is, you look at the entire universe and you pick some scale, and then as the universe expands, that scale expands with it. So formally, you have some metric which looks a lot like Minkowski space, although it can be flat, open, or closed. I don't care about the flat, open, or closed part. But the point is that your spatial coordinate, dx3, is multiplied by some a of t. And as time goes on, that scale factor is expanding. Okay, so you characterize how big the universe is by that factor a of t. And the most important quantity to keep track of, for the most part, is the Hubble parameter. And it's not a constant because the Hubble parameter can change as the universe expands, and does in general. But the Hubble constant has a lot of different meanings. The Hubble parameter has a lot of different meanings, and it's worth taking a moment to reflect on all of them. So first off, if you're an astronomer, h is a distance-velocity relationship. So that is Hubble's law, that the recession velocity of a distant galaxy is proportional to its distance, and vice versa. But that is not how particle physicists usually think of Hubble. Hubble is also, if you look at the units here, you can see that Hubble is a rate or an inverse time. And so we can think of this as a time scale which is the time scale on which the universe changes by order 1. Right? So in one Hubble time, the universe will have effectively doubled in size. So processes that happen on timescales that are much shorter than the Hubble time are things that you can treat the universe as effectively static, and processes that happen on timescales which are longer than the Hubble time, you need to take into account the fact that the universe is expanding. And lastly, h is also a distance scale. So you can take this and convert it into a distance scale, which is something like, in most cosmologies, the size of the universe. It's the horizon size, how big the universe is. And that can give you a scale of what sorts of distances can be important at any given era. Now, I will be caring about it most in the context of the second, which is I'll be caring about the universe where h is giving me a time scale for how much the universe changes, because we'll be talking a lot about equilibrium processes, things going into and out of equilibrium, and so the time scale we'll be comparing to is going to be the Hubble time. Okay? Now, in a flat universe, which we appear to live, at least to a good approximation in. In a flat universe, you have the FRW equation, which relates the expansion rate of the universe to rho, the energy density of the universe. So rho is just energy density divided by volume for the various components. So rho is a combination of matter, radiation, dark energy, and any other fluid you might include. So if you want to understand the time scale, that's equivalent to understanding what the universe is full of. Secondly, I'm sure you all know this, but you rewrite G Newton as a way of defining the Planck scale, which is approximately 1 over 10 to the 19 GeV squared. Now, for a given fluid rho, we characterize that rho by an equation of state, W. So you have the pressure, and you have your energy density, and you have your equation of state. Fortunately, I will not be dealing with pressure, so we will not be forced to distinguish my P's from my rhos. But we will for one moment, just to note that if you have a given equation of state, so a relationship between pressure and energy density, then you can describe the evolution of your fluid as something which goes like this scale factor to the 3W plus 1. So for instance, if you have W equal to minus 1, that's a cosmological constant, and rho is a constant. If you have W equals 0, so there's no pressure, it's just stuff, then that looks like dark matter, or ordinary matter in many cases. In that case, the energy density dilutes like volume. And if you have W equal to a third, that is radiation. And in that case, the energy density dilutes like a to the minus 4. Now, you can understand these evolutions intuitively. Obviously, if you have a cosmological constant, then that's energy density of space. So as the universe expands, the energy density doesn't dilute. And so if you look at the Hubble constant, well, if the energy density is not diluting, obviously the Hubble constant shouldn't change. And the energy density should not dilute. If you have dark matter, well, then you have a box, and that box has certain sides, and there's a certain amount of stuff in that box, and so when that box expands, the energy density, which is stuff divided by volume, well, the volume is increasing like a cubed, so the energy density is decreasing like a cubed. And for radiation, it's the same thing. You have a box full of photons. Well, as the edges of the box get larger, the number density of photons drops off like a cubed, but each individual photon also gets redshifted, and so the energy density of each photon decreases like 1 over a. So the energy density in radiation drops off like a to the minus 4. I'm not trying to really go into detail to describe that because you will have lectures by Scott Dodelson where he'll go into all sorts of things about cosmology. I just want to, for our purposes today, take note of this relationship, that understanding how fast the universe is expanding is related to energy density, and these are how these energy densities evolve. Well, effectively, the cosmological constant is saying that space itself has energy density, right? So if you compare it to, say, dark matter, in dark matter you say, well, look, I've got some box, right? And I take that box and I stretch out one side. That dilutes it by 1 factor of L. I stretch out this side by 1 factor of L by this factor of 1. So that's 1 over a cubed, right? But but if the space itself has energy density and I have a bigger box, well, the total amount of energy has now gone up with the box, right? So energy divided by volume has not changed. In essence, if you're just saying space itself has energy, then it's kind of intuitive. It's sort of, I'm sort of actually, it almost begs the question. I'm just saying to you, well, the energy density is constant because space just has energy density and nothing happens to it as the universe expands. So it's kind of sort of asserting it, but it also comes out from saying that W is equal to -1. You might want to say that you're assuming that it's constant, and that's telling you what W is. A lower bound or upper bound for W. So there's an upper bound from W, which is +1, which is where you're essentially all the energy density is in this pressure. A lower bound of -1 comes from trying to have some principles that you don't want gravity to be pathological. Now, from a phenomenological point of view, you can have W's less than -1 if you group things together in special ways. So what I mean is you don't actually have a fluid whose equation of state is less than -1. But if, for instance, dark matter had an equation of state which was negative, and I didn't appreciate that, then I might fool myself into thinking that the cosmological constant had an equation of state which was less than -1. So effectively, so in reality, you should treat this for most sane theories as a lower bound, -1. But it's not crazy to have theories where you might artificially extract an equation of state which is less than -1. Because somehow there's actually some other stuff in there which is diluting more slowly than you thought it was. And so you attribute that to dark energy actually growing. This is not something we particularly need to worry about, but it is something to take into account. Other questions? Feel free to ask Scott all these things too, because I mean that sincerely. So, what do we care about? We care about the fact that the energy densities, so we want to know how the energy densities of the fluids that we're talking about are going to evolve. So the energy density for a radiative relativistic fluid is just this. So it's just pi squared over 30 times g t to the fourth. G here is the number of degrees of freedom you have, so spin states or flavor states that you have of your typical type of matter. T is the temperature, and then depending on whether it's a boson or fermion, you pick up a prefactor of 1 or 7/8. Okay? But the heuristic is that if you have a fluid that's relativistic, that the energy density of that fluid goes as t to the fourth. And that should not be surprising because that's the only dimensionful scale you have in the problem. If I have a relativistic fluid, then its mass is irrelevant. So the only parameter I have is t. So it shouldn't surprise you that this is the energy density of that fluid. For a non-relativistic fluid, it's just the number density of that species times the mass of that species. This is not surprising. This is just saying I've got a bunch of stuff. Its kinetic energy is irrelevant, so its energy density is dominated by its rest energy. So it's just the number density of that stuff times the mass of that stuff. And the number density of that stuff, if it is in equilibrium, is this. We now have an additional parameter in the problem. So again, G is the number of degrees of freedom, M is the mass of the species, T is the temperature, and then the only other factor is this scale mu, which is the chemical potential, which can tell you whether or not you have, say, more particles than antiparticles. If you have a system where the particles are equal to the antiparticles, then mu vanishes, and it's just e to the minus m over t here. And the important point about this expression is, of course, that it drops off exponentially as the mass drops below the temperature. So if you have something which is in equilibrium and non-relativistic, it will become exponentially, vanishingly present when it is non-relativistic, unless there's a chemical potential to keep it present. Good. So the last thing that I want to assert in our cheat sheet is that the radiation energy density, which we just said was proportional to t to the fourth, and we said that the radiation energy scales as a to the minus 4, and you can, of course, combine these two things together to get the fact that t should scale like a to the minus 1, which is true in general, as long as there's no entropy production in the universe. And this is an important factor to keep in mind, because this means that we can treat temperature as a sort of time variable. Right? That the early universe is very hot, the late universe is very cold, and absent any entropy production, there is a monotonic relationship between these two things. So it's just as easy for me to talk about an era of the early universe in terms of the temperature of that universe as with the time at which that universe had been around.
Isn't there a square root or a square in that?
In which?
T to the temperature and time.
Oh yeah, this depends on cosmology. Yeah, absolutely, this depends on cosmology. I'm just trying to say here that they scale together inversely. But you're absolutely right. This is not an alpha. This is not a proportionality. And depending on whether it's matter dominated, or radiation dominated, or cosmological constant dominated, the relationship between these two things will change. So it's very, very important not to treat this as equality. I just simply mean that I can make this exchange intellectually to say that when I want to talk about a particular era of the universe, it is equivalent to talking about the temperature as it is to talking about the time. But a point well made. And so, given all of this, you can combine all these pieces together and note that then the Hubble constant is dominated by typically the radiation energy. So the energy density in a relativistic fluid is this g star times pi squared over 30, where g star takes into account that 1 or 7/8 factor. And t to the fourth is, of course, the temperature of the fluid, times, I don't have a g Newton in here. Let's put a g Newton in there. And so you can then write this, that the Hubble constant in the early universe is equal to 1.6 times t squared over m Planck times g star to the 1/2, or, as most people will treat it, g star to the 1/2 times t squared over m Planck, or as even more people will treat it, as just t squared over m Planck. When you're talking about early universe cosmology, usually you're talking about things that vary over orders and orders of magnitude, and so you're trying to determine whether something is much, much, much too large, much, much, much too small, or whether it happens to be in the region of interest. So you very often can get away of doing these sorts of order of magnitude estimates, and then only worrying about all the factors once you determine whether the precise details matter. But this is a very, very handy relationship. If you want to calculate what the rate is, Hubble rate is during the early universe, as long as the energy density of the universe is dominated by radiation, which it was prior to z of about 3,000, then this is your shorthand for the Hubble constant. Questions about any of this? Okay, good. Then, given that, we can do one last element of our cheat sheet, which is questions of equilibrium. And of course, we'll derive this more properly in a little bit. But the critical question then for any process is a comparison between the rate of some process and the Hubble rate. Okay? So I'll show you an example of a specific process in a second. But this is the question you're always, always, always asking. Is this rate bigger than Hubble or less than Hubble? If it is bigger than Hubble, then that is an equilibrium process with exceptions. If no, then this is not an equilibrium process. And when you're talking about the early universe, the critical questions you're always asking are, what are the states that are being produced, and what are the processes which are in equilibrium? And so this is a question that we'll ask ourselves over and over and over again. Or you in your life will ask yourself over and over and over again. Now, let's consider just a very, very simple example of that so you know what I'm talking about. You can consider the following process. Consider neutrinos annihilating to E plus E minus through a Z boson. Well, this is a nice situation because if you go to the very, very early universe, you know that the cross-section for this process should go like 1 over mz to the fourth, or like G Fermi squared. So if you want to get your rates and dimensions right, the number density times the cross-section times the velocity should go like G Fermi squared times t to the fifth. Because this is a rate, and this should have dimension 1. Okay? So in the spirit of just doing order of magnitude estimates, I ask a question here, which is, suppose I have a relativistic neutrino or antineutrino that's flying through the early universe, and I want to ask, what is the rate for it to find another neutrino and annihilate into, say, E plus E minus? Okay? So the rate for that to happen is, well, the number density of neutrinos that I'm going to encounter times the cross-section times the velocity, which is c, and then this is what you get. So you ask this question. I want to compare that rate to the Hubble rate. So I'll take G Fermi squared t to the fifth. I'll set that equal to Hubble, which, as I said before, at this level of approximation is t squared over m Planck. And then you can solve this for a temperature, which is 1 over G Fermi squared m Planck to the 1/3, or approximately 1 MeV. Very, very approximately, although surprisingly accurate. So what this tells you then is if I'm at temperatures which are higher than 1 MeV, then I can reasonably say that this is an equilibrium process. And if I'm at temperatures below an MeV, then this process is not an equilibrium process. This is confusing a little bit because an MeV just happens to be right around the mass of my final state. So this is one of those situations where you really, really actually should do a proper calculation to get it right. But this shows you that you can treat neutrinos as equilibrium particles at temperatures above the electron mass, and below the electron mass they are not. We'll be doing calculations like this in the context of dark matter, of course. And since we're discussing equilibrium, let me emphasize, just so that this is really driven into your head, yes?
Could we have an approximate conversion from MeV to Kelvin?
Oh, you're killing me. Let's see. A 40th of an EV is room temperature, right? So that's 300 Kelvin. And after that, you multiply. I will find that out and tell you this afternoon. But
So 12,000 Kelvin per EV.
what's that? 12,000 Kelvin in 1 EV? There you go. Yeah, I'm trying to think of what temperatures I know the reference to, but that's, I don't, yeah.
That's 12 billion Kelvin.
Oh, it's very, very hot. Oh, yeah, it's very, very hot. It's hotter than any system that you'll find astrophysically. Yeah. Well, that's not entirely true. You could find astrophysical systems that reach this temperature, but not anything which is in steady state. Few 10 to the 10 Kelvin. There you go. Very hot. Thank you. Feel free if I am saying something and I don't know the answer. I am not the source of all knowledge, certainly. And that is some of it that clearly we've evidenced that right off the bat. So as we're talking about decoupling, let me emphasize that there's two types of decoupling. You have chemical decoupling and you have kinetic decoupling. Chemical decoupling means that the number density of your species is in equilibrium. while kinetic decoupling just means that the temperature of that species is in equilibrium. And usually, although not always, if you're in equilibrium with one, you're in equilibrium with the other, but very often you'll have a situation where you'll decouple, say, chemically first, and then decouple kinetically later. And it's important to make these distinctions because different parts of decoupling can be relevant for different processes. Good. Questions about any of this? Yeah. I try to be a little bit careful when I say the words thermal because, as we'll see in later examples, people toss the word thermal around quite cavalierly, and I will probably toss it around quite cavalierly too. So I try to not use thermal when I can avoid it, because sometimes people will say thermal equilibrium and they really mean chemical equilibrium. Sometimes people will say thermal equilibrium and they really mean kinetic equilibrium. So I'm just trying to be clear on what I'm distinguishing here. Good. All right. Well, that's what he's saying. He's saying that usually can you think of that as thermal equilibrium? And to the extent that if you mean thermal equilibrium, you're talking about the temperature being in equilibrium, then yes. But what I'm saying is that some people will use the phrase thermal equilibrium. You'll read papers where people will use the phrase thermal equilibrium in a way that doesn't actually mean that. So I prefer to be judicious in my use of the word thermal equilibrium because it's just important to be clear what you're saying. Clear to be clear what I'm saying. Okay, good. Yeah. A Z propagator, yeah. Yeah, now these temperatures are sufficiently low that I don't think that is going to be relevant here. I mean, you're talking about MEV temperatures, so that should be pretty small. Oh, if I go up to very, very high temperatures, then this cross-section, if I go to temperatures which are much, much higher than MZ, then this cross-section will shift over to being 1 over T to the, well, it'll become 1 over T squared, effectively. But you'll see that also will keep you in equilibrium as long as, well, it's a subtle point. The point is, as the universe comes, this will be in equilibrium for long enough. There are certainly cases where you will not be in equilibrium until a specific temperature, but it's very, very, very high. So in all cases that you'll almost ever deal with, you'll be in equilibrium here. Let's discuss that in a little bit, because you're talking about a situation which is related to the energy scaling of the cross-section. And so here I'm dealing with a situation where the cross-section has an energy dependence like this. You're talking about moving it into a regime where the cross-section actually has a different energy dependence, which actually corresponds to a different scenario. And we'll discuss that. So let's just hold off on that, and believe me, then I tell you that we will get to it. But a totally valid question. So that's our cheat sheet. That's now you know everything you need to know about cosmology. H goes like T squared over M Planck in the early universe. The question of freeze out is dictated by setting the rate of some process equal to the Hubble constant. And that's a calculation we'll do again and again. So let's now change gears and talk a bit about what we do and what we don't know about dark matter. Now, you'll hear lectures on direct detection, indirect detection, observations. Manoj will talk about observations, so I'm going to try and be only quoting the principal results here. But it's important to start here, because when you're constructing theories of dark matter, talking about theories of dark matter, you really want to know what are you, in the back of your mind, trying to make sure that you're consistent with when you're writing it down. Now, this could be because you're an experimentalist and you want to know whether or not that model is ruled out, or it could be because you're a theorist and you want to know whether the model that you're starting to consider is dead from the get-go. And so the thing that we should recognize is that we know lots of negatives, but essentially 0 positives. All right, so we know a lot about what dark matter isn't. We know nothing about what dark matter is. And this is something that you should this is another one of those things that you should really drill into your brain, because you will hear people, probably including me, who talk about dark matter theories, and they'll get up and they'll say things like, oh, dark matter usually blah, blah, blah. Or typical models of dark matter, blah, 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 right? And if we are doing that, if you hear one of us saying that, then either we are trapped in our own assumptions or we are trying to sell you something. So be very, very cautious when anybody tells you how dark matter typically behaves, because how dark matter typically behaves is not a well-known thing. Let me emphasize that with a little bit of history. If you think about the evolution of dark matter models with time, you can think about the different properties that dark matter had. If you go back prior to the 1930s, of course, there was no favored dark matter candidate, and it had no properties, right? There was not any need to consider dark matter. So everything would have been considered an exotic candidate of dark matter. In the 70s and 80s, when you started getting qualitative information as well as some quantitative information on the properties of dark matter, I think the favorite candidate would have been gas or brown dwarfs, Jupiters, things like this. And its properties were that of ordinary matter. Now, ordinary matter comes in many different phases. So ordinary matter has many, many different properties, but that would have been the characteristics you would have looked for. Now, as time went on, I think people began to appreciate that exotic models of dark matter were probably needed. And so in the 80s and 90s, the favorite candidate would have most likely been a heavy neutrino. And that's a weakly interacting particle with a capital W. It couples to the W boson. And it is hot, which is to say that when it was formed, it was relativistic. In the 90s and onward, probably the most favored candidate would have been the neutralino, which is a very weakly interacting and cold. And the reason why I say that this is probably was the most favored candidate in that period is you can go back and read papers from the 90s and early 2000s where people will use dark matter and neutralino interchangeably. It was that ingrained into people's minds. Yes? So if it was back then, it was closer, depending on whether there's 1 or 3, it would have been around 30 eV. Once you have the cosmological constant, you want it to be more like around 10 eV. And then if you want it to be multiple generations. But at this point, once you know that there's cosmological constant, you know it's not hot dark matter, so you don't want it to be a neutrino anyway. But you're sort of in the sort of 30 eV range. Well, we'll discuss that in a second. Give me 1 second. Give me 1 second. That's on my next page of notes. That's right. That's right. And going from here to here. But I mean, you also go from here to here. Even if you didn't know anything about structure, just our knowledge of neutrinos has already told you that the neutrino can't account for the dark matter in the universe, right? If you combine the neutrino oscillation experiments with the tritium endpoint measurements of the mass of the electron neutrino, you already know that 3 neutrinos together can't give you enough mass to give you the dark matter. No. That was probably just a little meandering. What I was saying is that once you know there's a cosmological constant, the number you're shooting for dark matter has dropped by a factor of 3, right? Back in this day, people wanted omega dark matter to be 1. And now you want omega dark matter to be like a quarter. And so since the amount of dark matter you have is scaling with your mass, the mass of the neutrino you would want today is different from the mass of the neutrino you'd want then. But on the other hand, we don't want a neutrino as dark matter anyway because of structure problems. The reason why I bring this up here is not really to emphasize any lovely things about neutrinos or neutralinos, but just to emphasize that if you talk to people in these different eras about what is a conventional model, their ideas change. So if you talk to somebody in this era, about a neutralino, they will say, oh, yes, a neutralino is a very, very conventional model, and it's very ordinary, and you don't pay any price for talking about it. But if you want to, say, talk about dark forces or something like that, you're a very, very strange person, and, you should be controlled. But if you go back to this era and you want to talk about neutralinos, people also thought that neutralinos were very, very exotic models, and that you should be very careful before jumping to some conclusion of considering some exotic candidate when you have a perfectly good candidate like this. All I mean to say is that our ideas of what is a natural model of dark matter have changed. And so you should be, again, very careful if somebody tells you this is what a natural dark matter model is, because that changes too. So let's talk about evidence of dark matter, which comes to this question of what happened between 1930s. Now, Manoj will, of course, talk about all of this in gross detail, but he also will not particularly care about it because he'll be focused on what's going on now. But so our evidence of dark matter starts with Zwicky in the 30s and the Coma cluster. And the issue there was that you have a cluster of galaxies These are galaxies. And you can look at their motions. Really, obviously, you can't actually look at their transverse motions. You're looking at their line-of-sight motions, but I can't draw line-of-sight motions. And you use the virial theorem to tell you that the characteristic kinetic energy of one of these things should be set by their potential, which is set by sort of the average gravitational potential. So this then allows you to relate the dispersion velocity to the total mass in this cluster system. This is just simply saying that if there's a lot of mass there, then things will be moving very fast, and if there's very little mass in there, things will be moving very slowly. So you measure how fast they're moving, and you use that to tell you how much mass is there, and you come out by finding that there is a tremendous amount of mass there that you're not observing. The mass-to-light ratio is something like 100. Now, this shouldn't surprise you too much because you don't expect all mass to be in the form where it's luminous, right? You think stars have some mass, but there should be a lot of mass there that's not luminous. So it shouldn't necessarily surprise you that there is some mass which is not luminous. So the reason why I take this distinction between 1930s and the 70s and 80s is because in the 70s and 80s, you have here Rubin and collaborators and other people who start looking at rotation curves of galaxies. So you look at some face-on spiral galaxy like this, and you look at objects at greater and greater distances from the center. And what you expect is that you should be able to map how fast these things are spinning. Actually, you look at these things edge-on, so you look at them from the side so you can measure this well. And you expect a curve that looks something like that. Okay, so as you go farther and farther and farther away, since all the mass is concentrated here, the gravitational force should be dropping off, and so these things should be spinning more and more slowly as you get out to the outer regions here. But what you actually find when you look at the data is a flattening of the rotation curve. That these things out here actually all have the same velocity, and so this difference here should be interpreted as dark matter. And this is the point where you actually need to start thinking about dark matter as something other than ordinary matter, at least in the sense that ordinary matter here, a lot of the visible matter, has cooled and collapsed into this galaxy where there's some amount of matter of some form which has persisted uncooled in a halo around the galaxy, because this extends out 10 times the radius of this galaxy. Okay? So there should be something out there that has different sorts of cooling properties than the ordinary matter that you see. And that's why I'm saying there's a beginning of the change of whether you should start considering new pieces of data. Now, at this point, we have a lot more data. So that was 1 and 2. But now we have a tremendous other amounts of data that tell us that dark matter is there. We have gravitational lensing. So you have some cluster of galaxies. These are galaxies here. Then you have some distant object over here. And its image can be lensed. This can be a strong lens or a weak lens, but you can infer the amount of mass here from looking at how these images are distorted, and that tells you that there should be a lot of mass which is in the form of dark matter. You can look at the power spectrum of the CMB or of matter from large-scale structures. So you can go out, you're all very familiar with the very famous plot from Planck or from WMAP, looking at the acoustic oscillations of the temperature spectrum in the CMB. But you can also look at the fluctuations in the overall density of matter on different scales of the universe. So if you look at, say, megaparsec scales, you can ask how large are the fluctuations of delta rho over rho on megaparsec scales, on kiloparsec scales, on gigaparsec scales. And by comparing that to theory, you can see that you get a curve that agrees with what you would have expected if there were dark matter. And in particular, now we've actually gotten good enough that we can see these baryon acoustic oscillations. So we can see the fact that in the early universe, dark matter or ordinary matter is pressing off of itself. And that also tells us that there should be some stuff out there that is not dark matter. And this is a very, very important difference. Yeah.
So I want to ask, can you estimate the mass of these different pieces of evidence so that they all coincide?
So this allows you to estimate the mass in a specific set of galaxies. But that is tough to use to get a total estimate of the energy density of dark matter in the universe. With lensing and looking at the properties of clusters, you can do something looking at the mass to light ratio as a function of size. And as you go out to larger and larger size, you can see that it's asymptoting, and then use that as a proxy to how much mass there should be in dark matter at these large scales. And that does agree. These are basically different ways of looking at the same data set. So they both together give you a number which is consistent, which is omega dark matter of about 0.25. So everything up to this point is consistent. And when Scott talks, he'll of course talk about the concordance cosmology, where there's a lot of different pieces. There's your supernova data, there's your CMB data, there's your structure formation data, there's your BAO data, and all these things do together. You have basically in the standard cosmology, where you assume that it's a flat universe, you have two parameters, omega matter and omega lambda, and you have multiple pieces of data, and they all overlap non-trivially. So in that sense, they're all consistent. But on the other hand, each one of them is usually consistent with a range of values. Yeah. Oh. So all I'm saying here is that when you go out and you do these galaxy surveys or Lyman alpha surveys, you're looking at the sizes of fluctuations of delta rho over rho, more or less, on different scales. And at very, very large scales, the universe is still very, very linear. Once you get down to about 10 megaparsecs and smaller, the universe is very, very nonlinear. This particular turnover here corresponds to how structure evolves in the early universe during matter-dominated era and radiation-dominated era. This little kink here, that's the baryon acoustic oscillation. So that has to do with the fact that if you look at the power spectrum of baryons in the early universe, they're not just freely falling into gravitational potentials. When they're in equilibrium, well, when they're tightly coupled to the photon fluid and they start falling into overdensities, they have a pressure that pushes back. And so there's a signal that you can see. And this gives you an independent measurement of how much baryonic matter is out there. So if say, all the matter in the universe were baryons, you'd get a very, very, very different value for this. And then the last thing that I just want to point to is Big Bang nucleosynthesis. Big Bang and nucleosynthesis, so you can go out and measure the abundances of lithium, deuterium, helium, and so on. You can compare that to theory, and these things are all in agreement, more or less, with a baryon to photon ratio of 6 times 10 to the minus 9, which gives you omega baryon of about 0.04. Now, that's obviously not a measurement of dark matter itself. This is a measurement of how many baryons are out there. But this is a very, very, very difficult thing to fight with if you try to explain dark matter with baryons, because this tells you that at temperatures around an MeV, the universe had an amount of ordinary matter, which was about 0.04 of omega. And if you want dark matter to be 0.25, then you somehow need to explain that discrepancy. And the fact that when you look at the data from BAO and you look at the data from the CMB, all of those things are 100% consistent with this value. It reinforces this idea that this is how much baryonic matter is there in the universe. So there should be a sizable contribution of dark matter. The important thing I want to emphasize about these things is that these are very, very disparate pieces of data. You have CMB, which is measuring the properties of the universe at Z of around 1,000. You have structure formation, and these things, measurements here, which are measuring sort of an integrated effect of the universe from mostly around 1,000 to now. You have the CMB, or excuse me, the BBN, which is telling you what the universe was like at an MeV. You have lensing, which is a measurement of structures that exist out there. And the bullet cluster, which we'll talk about in a second, which measures the separation between ordinary matter. And all these things, different areas of the universe, different scales, different techniques, all consistently point to this idea that omega baryon is around 0.04 and omega dark matter is around 1/4. And I want to emphasize this because at this point, dark matter is the conservative idea. People like to say, like, oh, aren't you invoking an ether? Shouldn't you be very concerned that you're inventing something that you can't see? And I think the answer is no. The idea that there is matter you can't see is a very, very conservative idea. We already know there's neutrinos. We can't see them. They have some mass. That's not the dark matter. But it's very, very unsurprising that there should be stuff that we can't see. So the idea that you want to modify gravity is the exotic idea. And I really, really want to emphasize that. I'm not saying it's a bad idea to try and pursue that. I'm saying that's the exotic idea. The conservative idea at this point is to study dark matter. Yeah. Well, a lot of these techniques work by having an ensemble of, if you're looking about weak lensing measurements, you can have an ensemble of galaxies, and you can look for some sort of like, on average, shearing, right? If I see an individual object, it's hard for me to tell whether or not that object has been lensed or whether I'm just looking at an object that looks like that. But if you have, say, a halo, and I study all of the galaxies that are coming around it that are having their images lensed, then I'll see, statistically, I can see an effect that tends to be telling me that there's a lensing going on there. So it's not relying on those particular measurements are not relying on any specific galaxy to be lensed, but really an ensemble of them. So I think that's pretty robust. If that were the only piece of data that was telling you there was dark matter, maybe we would beat it down. But I think the fact that all these things are lining up consistently gives you a lot of confidence. Okay. Good. So hopefully you believe me that there is dark matter. So let's talk about what we know about dark matter. So you're going to sit down and you're going to build a model of dark matter, and you want to know what requirements you're going to place on it. So, 0. It should be massive. So that is that the equation of state should be approximately equal to 0. So massive, I mean it should act like cold matter. It should be pressureless. And you can ask this question, well, what does that mean, right? Because, for instance, even neutrinos, massive neutrinos today are like this, have equation of state 0. They've cooled down, at least the heavier two generations have cooled down to the point where they act like matter, cold matter. So what I really mean is that since temperatures of around a KeV, you should have had an equation of state of 0. So prior to KeV, if you're talking about temperatures above a KeV, then it's perfectly OK for dark matter to have been relativistic as long as around a KeV it transitioned and became cold. Okay? And that's based on the fact that when you get to these small scales, our ability to calculate things is limited. It's not very, very nonlinear there, and so people don't trust the data as much down there, and so there are limits to what you can do. But there's no sign of dark acoustic oscillations. There's no sign of very sizable pressure later in the universe. So to a very good approximation, this should be true. So that dark matter is redshifting like a to the minus third. Secondly, no, M dark matter doesn't have to be greater than KeV because it doesn't have to necessarily have been in thermal equilibrium. So, for instance, axions have mass which is much, much less than a KeV. What you want to make sure is that when the universe has a temperature of a KeV, that at that point, dark matter is cold and pressureless. Wherever it came from, however it formed, when you get to a temperature of a KeV, it better be cold. Because if it were hot, then it would free stream, and we would not see structures that started forming in that era.
So this is T gamma.
This is T gamma. Yeah, I'm sorry. When I say T, I'm really talking about sort of the background, but that's a very important point. T of the background plasma.
Do we have a mass? So in some sense, this also takes into account coupling with.
Well, here I'm just using T as a clock. So I'm just saying that I can look at all the different structures in the universe, and I can say these structures started forming at T of 10 eV, and these ones started forming at T of 1 eV, and these started forming at 0.1 eV. So these all look like dark matter. These all look like cold dark matter. So it better have been cold dark matter all these eras. And I can say, well, at what point, how far, as I go back here, these structures started forming at T of 100 eV. These ones started forming at T of 1 keV. But dark matter is kind of doing its own thing over here, decoupled from the photon bath at that point.
And there is no real limit of mass, lower bound of mass. We just know it's not.
So this is actually a very interesting question, and I can show you if I get my scales correct a little bit later. I can show you. Basically, you have two lower limits on the mass of dark matter. One of them is that the dark matter better have a mass of greater than about 10 to the minus 22 electron volts if it's a scalar. Let me just write that down. That's right. So a scalar better have a mass greater than about 10 to the minus 22 eV. And a fermion better have a mass greater than about 100 eV. Although this has been updated, I should find the most current specific, but it's maybe a little bit stronger than this now. And this basically, the top of this comes from just the fact that you see galaxies that have sizes which are this big. And if you had a field whose Compton wavelength was bigger than that galaxy, you'd never be able to fit it inside the galaxy itself. So you couldn't have structures that are as small as we see if the dark matter mass was smaller than this. For fermions, you run into a similar problem, except for instead of worrying about the Compton wavelength, you're just talking about Pauli blocking. So if I want to stack cold matter inside a galaxy, and I've just been filling all of the states up to the point where I have enough to explain the mass of the galaxy, but still be bound inside the gravitational potential, then I need to have the mass greater than 100 eV. And this is known as Tremaine gun. This doesn't have a name. The paper is called Cold Fuzzy Dark Matter, and I happen to know because one of my colleagues is on it. But I don't think he's the other people, but I find you the paper. Yeah, it's called Cold Fuzzy Dark Matter, where they point out this limit. And Andrei Gruzanov is one of the authors. Yeah. Huh?
The first limit doesn't seem very constraining.
It doesn't seem very constraining now. It doesn't. Okay. The second thing, so this should not surprise you. It's called dark matter. So it should be matter. It should act like matter. We also say it's dark. So, unsurprisingly, it should be non-interacting with photons. So how non-interacting with photons should it be? Well, so let me show you this plot first. So the biggest constraints on how much this stuff is charged is related to whether or not this stuff is tightly coupled to the photon plasma in the early universe. If it's very, very tightly coupled to the photons, then just like you have baryon acoustic oscillations, the dark matter will also be oscillating along with the baryons. And you can't have that because you'll see things that would have changed that signal significantly. So this is a paper by these people in 2003 where they're worried about this question. So if you have dark matter that has a tiny, tiny, tiny charge, which is theoretically possible, you need to worry about whether it has come into tight coupling with the photon plasma. And that's dependent on a relationship between its charge and its mass. Because I have a very, very, very massive particle, and it's getting bombarded by very low energy photons, that's not going to tightly couple it unless I get smacked many, 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 many times. On the other hand, if I have a lighter particle, then I need to be smacked fewer times to be tightly coupled to the photons. So lighter particles can have a lower charge and be tightly coupled. Heavier particles need to have a larger charge to be tightly coupled. And so here's the charge, here's the mass, and this black line here is the one that you should pay attention to. Basically, everything on this side of that line is tightly coupled. Okay? So once you are tightly coupled, then you are effectively constrained. And if you take the Planck data, you can make limits on those constraints. And this is some of those similar authors, at least these two are there, and 13 looking at the Planck data at the time. And you can marginalize over omega baryon, over m nu, over the number of neutrinos, because you might want to deviate from this lambda CDM. But omega MCP is omega of millicharged particles. Okay? So this is essentially constraints on anything which is on that side of that black line, anything which is tightly coupled to the photon plasma. And more or less, all these things give you limits if you marginalize over your other parameters, which tell you that this stuff better be less than 10 to the minus 3. Omega millicharged particle better be less than about 10 to the minus 3. Okay? So you can have stuff which is millicharged and tightly coupled to the photon baryon plasma, as long as it has an omega less than 10 to the minus 3. Or if you want to have something which has omega greater than 10 to the minus 3, so is actually dark matter, then you want to live on this side of this line. Okay? So you can either be very massive or have a very, very small electric charge. Good. Sorry? So as you make the thing more massive, so what is this? This tells you is if I want to be tightly coupled to the photon baryon plasma, then if I'm very massive, I better have a larger charge. Okay? Because if I'm, say, 10 to the 12 EV and I have a 10 to the 6, 10 to the minus 6 charge, then that's not enough to tightly couple me. So heavier masses, in order to be coupled, need a larger charge. Lighter masses, in order to be tightly coupled. Yeah. The constraint on the other plot? The constraint on this plot is basically under the assumption that you are on the right side of that line. So these constraints are just, let's assume that you are tightly coupled. How much can you have? And this is a statement of how much you can have. So if you're on the left side of that line, basically, and there's some transition region, but basically once you're on the left side of that line, you're fine. When you're on the right side of that line, you better have omega less than 10 to the minus 3. Okay.
Cosmology limits. So if you had, there are additional limits from the derivations of indirect detection or something.
So, so there are a variety of. It becomes very, very model dependent. This down here, this is out of date. But for instance, this here, these are AC. These are accelerator constraints. They're in general not as relevant as the for a massless photon, are generally not as strong as with you have the cosmological limits. If you have a massive dark photon, then the the terrestrial experiments can beat them out. But right now I'm just talking about its coupling to actual photons. To real photons.
So is the statement that no particle experiment has ever proved viable?
Yeah, I think that would be that's how I would read this plot. Consistent with the CMB, you cannot detect something that has that small of a charge or that high of a mass. Yeah. I mean actual charge. I mean literally electric charge here. So I'm talking about that it's coupling to the vector current, Q, psi bar, gamma mu, psi, a mu. I'm talking about that coupling. There, you can have dipole interactions, which are very, very unconstrained, but I'm really just talking about its literal electric charge. Okay, good. So it has to be matter. It has to be dark. You can be unsurprised that the next thing I'm going to say is that it has to be cold. So we've discussed this now quite a bit. And the idea is that if in the early universe you have an overdensity of particles and they're hot, then those particles will free stream out of that overdensity and they'll erase inhomogeneities. So if dark matter was hot in the early universe, you lose small scale structure, and that tells you that it must have been cold at some era. And like we said before, that the temperature should have been around a keV. Below that, it better be cold. There's a specific paper by these authors, Sarkar, Das, and Sethi, where they study this in more detail. And they find that more or less dark matter should have been cold prior to, this is actually 23 eV, this is 200 eV. So if you use just the SDSS data, then, and you look at structure just from galaxies, then dark matter better have been cold prior to 23 eV. If you go and use Lyman alpha data, then it better have been cold prior to 200 eV. In most models, there's a transition region where you go from being hot to being cold. And so when I say you better have been cold at a keV, that's usually because you'll end up being warm at these scales if you are going from hot to cold. This one or this one? Oh, so what they're saying is that dark matter, if you look back in redshift, Z, that dark matter better have been cold prior to Z of 10 to the 5th, after 10 to the 5th, based on the SDS data. So at 10 to the 6th, dark matter could have been hot and fine. But at 10 to the 5th, it better be acting like cold dark matter. If you use the Lyman alpha data, then you can say that dark matter better have been cold after 9 times 10 to the 5th. I guess my way I'm writing the inequalities is fine. Prior to this, it's fine if it's hot. Prior to this, it's fine if it's hot. But after this, later than this, it better be acting like cold dark matter.
This is the corresponding temperature of the dimension.
That's right. Z of 10 to the 5 is 23 eV. Z of 9 10 to the 5 is about 200 eV.
I'm confused about this with the other statement. Aren't
These are basically the same statement. This is just a more quantitative way and telling you what the data I'm using to get to it is. Okay. So dark matter has to be matter. It has to be cold. It has to be dark. And if you think about what the general framework we always talk about is, it's CCDM, cold, collisionless, dark matter. So the last constraint that you really need to worry about is non-interacting. So to a very, very good approximation, you can just ask this question: under what circumstances does n sigma v tau equal to 1, where tau is some characteristic time scale of either the universe or a galaxy. And if you have scatterings which are equal to or greater than 1, then that is probably excluded. So cold collisionless dark matter works well when you look at simulations, when you look at your linear theory. So anytime you start having your average dark matter particle scatter a single time, usually that's a bad thing. So if you want to ask a question, what are the limits on a given cross-section, you just ask this question. What is the likelihood that it would have scattered one time in some dynamical period? And you can look at, say, the Milky Way, and you get something like 10 to the minus 24 centimeters squared per TeV. You can look at the bullet cluster, where you see these two systems colliding, and you can ask what those constraints give you. And that gives you a limit of a cross-section which is less than 0.47 centimeters squared per gram, which is effectively a cross-section of 24 centimeters squared per second for a GeV mass.
So that's sigma over m dark matter in the second line?
This is sigma over m. Yeah, thank you. I write this in both these ways because if you look in the astronomical community, they will write all of their results like this in centimeters squared per gram. I have no idea how to think about that. That's what it is in.
This is sigma dark matter to dark matter.
This is sigma dark matter to dark matter. The cross-section for dark matter is scatter off of itself. There are additional limits on long-range interactions. And this is a somewhat controversial constraint, but I think it's important to keep in mind. And that is from equivalence principle violations. So if you look at the Milky Way, here's the Milky Way, and you have these dwarf galaxies which are orbiting around us. And if the gravitational forces that dark matter felt were different from the gravitational forces that ordinary matter feels, then you would have dark matter either leading or lagging the orbits of the baryonic matter, right? So if you kind of think of them being pulled in an orbit around the Milky Way, if there's a difference between their interactions, then if the dark matter is leading, then the baryonic matter will kind of lag behind, and you'll get some sort of stream of stellar debris coming from behind the dwarf galaxy. And you can get a similar property if the dark matter is lagging. This is from Kesden and Kamienkowski. And they claim, they parameterize it in terms of this number b, which they say has to be less than 0.2. And this is the strength of a long-range force relative to gravity. Okay. So if you want to have some very, very galaxy-long interaction, it needs to be subgravitational in strength. And then the very, 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 very last thing that I'm going to require of dark matter is that it be stable.
Sorry, what is B in terms of fundamental parameters, like in terms of actual model?
It's B is so if you think about it in terms of a scalar interaction, that's probably the easiest way to do it. Then B would be something like m divided by m Planck. So it would be the strength of the coupling to the scalar field relative to what it would be for gravity. Okay, right? Because the dark matter interaction should be something like g Newton times m dark matter squared, and so this would be the coefficient in front of that Yukawa. That's right. That's right. This is the constraint. The constraint is if dark matter has a dark matter only force, that is galactic in size, then that force better be less than approximately gravitational strength. Otherwise, you will have these disruptions of your dwarf galaxies. And I think that people might quibble with this particular value, but I think it actually is very, very true that if there were a very, very different gravitational force for dark matter versus baryons, that you would disrupt these dwarf galaxy systems. Why would you have this kind of a model, are you asking?
No, I'm saying, why does it have to be gravitational? This is not assuming any. This is not assuming gravitational.
This is not assuming gravitational. The statement is just that if you have something which is interacting, then the relative comparison is to gravitational force, because the gravitational strength is what's dictating the dynamics that you've observed. So it shouldn't surprise you that if you change the dynamics by an order 1 amount between ordinary matter and dark matter, that would be inconsistent with the data.
So it's saying like mass less than M plane, is that the same thing? So it's about like B being the mass of the particle over M plane, so it's kind of like the mass of the dark matter being less than M.
Well, the mass of the dark matter should definitely be less than M Planck for any particle model.
Yes. I was trying to understand how constraining that is.
No. This is about so what I'm saying is that if I have, say, a dark matter particle, and it has some Yukawa coupling, right? Then that Yukawa coupling is going to be something like, let's say, M divided by M Planck. Okay? Let me just call it that to parameterize it. And then the relative strength of these two of this kind of a process here is going to be something like, and let me put a coefficient here. Then the size of this interaction is going to be lambda squared M squared over M Planck times, if you want to put it in terms of a potential, 1 over R, right? So a scalar and attractive Yukawa potential. And so this then is telling me how strong that is relative to gravity. Okay. So if it's gravitational strength, if my Yukawa coupling, if I have a massless scalar in this particular case, and my Yukawa coupling to it is larger than or comparable to a gravitational strength interaction, so my mass divided by M Planck, then that would be ruled out. And then, yeah. This is setting a limit on the long-range dark matter self-interaction. So you have structure properties and the bullet cluster, where you look at two systems which have actually collided or have had an opportunity to collide, and that's a limit on the short-distance dark matter scattering, okay? Where if you have a sizable number of scatterings, then you will start cooling the system off or transferring energy from one part of the system to the other that will be in conflict with what's observed. And so that's where you get this. That's where you get this limit, right? That one is about if I've got like the whole chunk of dark matter interacting with this whole other chunk of dark matter through some coherent force as it's going around the orbit. Now, as far as it being charged, if you mean electrically charged, then that's the plasma limit.
Oh, I can have like really tiny charge.
Well, so now you're getting into some very, very specific details of the model, because if dark matter has a really, really tiny charge, the universe, because electromagnetism appears to be an intact gauge symmetry, then I better have equal amounts of positive and negative dark matter. And then you have to ask the question about, well, are these things then going to combine together to form, on average neutral systems, which is what you'd expect. You wouldn't expect to have, lots of segregation between positively charged dark matter and negatively charged electrically charged dark matter. You probably expect to have them all mixed up. So even if they did have some 10 to the minus 11 coupling, say, or 10 to the minus 4, probably the dwarf galaxy is electrically neutral. So even if it is charged, then it's probably okay. Yeah. Yeah, so that's velocity dependent. We'll talk about that a little bit later. This one was, the analysis was really done in the context of comparing it to gravity, so I think they really treated it as a 1 over R potential. So that would have been a velocity independent interaction. But, yeah. Yeah, that's right. So if you have some... Yeah, effectively, yeah. If you kind of think of, you've got this body of dark matter, and then ordinary matter is inside of it, if the equivalence principle holds, then they're both going to go around the central potential together, right? And yes, the dark matter is holding that ordinary matter bound inside of it, but it doesn't need to really worry about this additional acceleration because the equivalence principle keeps everything together, right? You effectively get to just treat this system as though it's a free system and ask whether its dynamics are okay. Once I start saying that I have equivalence principle violations, then yeah, the dark matter halo is going to want to orbit faster than the ordinary matter, and I now need to worry about whether the gravitational attraction of the dark matter in that halo is enough to keep this matter bound inside of it as it goes around. And if it's not enough, then it'll get disrupted. And that's basically where that constraint comes from.
What if there are different kinds of Lorentz forces which have opposite effects as cancel out? In this case, can I put any constraint on this?
Well, that would essentially be akin to this electromagnetic case, right, where you have positively and negative charges and they cancel out. At that point, it's more of a question about if it's something like that, then you have to worry about constraints from things like either whether you end up with something that gives you something that, like this, if it's an actual electric charge, or there are limits on dark acoustic oscillations, which are somewhat weak, but you can worry about those as well. But those limits are in general weaker.
Might have astrophysical limits from photons.
So most of the limits in that kind of a situation come usually from this sort of constraint. Usually that's what you get, is just sort of like dark matter interaction. And then you just need to look at, if you have multiple different types of dark matter, then it's a question about what fraction it is and the size of the cross-section. And yeah, but it ends up getting folded into this kind of a limit, because we're talking about a dark matter scattering cross-section. So let me just say the one very, very last thing, because we're over time. And that is, I said I want this to be stable. Yes. So what do I mean by stable? Well, so there was actually a very, very nice recent paper. And I'll write down the authors in a second because I realize that I've miswritten the first author's name. So it would be rude to write the second and third author's names and incorrectly spell the first author. So I'll just give you this reference number, where they find that if you have dark matter, which is decaying, that the fraction of dark matter which is decaying times the rate at which it's decaying should be less than 6.3 times 10 to the minus 3 gigayear. This is for invisibly decaying dark matter. I want to stress that. If dark matter decays into ordinary visible particles, photons, things like that, then there are all sorts of constraints that vary from mode by mode. And that usually you test from indirect detection. And Tracy can tell you all about that. This is simply a question of what happens if dark matter is decaying into invisible particles. And so it doesn't actually evolve like ordinary matter. It has a slightly different equation of state because it's transferring some of its energy density to radiation. And so it's effectively redshifting. F is the fraction of decaying cold dark matter, and this is the rate of decaying cold dark matter. So you could, for instance, have all of the dark matter be decaying, in which case it has to have a lifespan which is greater than about 10 times the age of the universe. Or you can have a fraction of it be decaying, in which case you can have more of it be decaying. But this is all just a statement of precisely how much you're changing the equation of state of the dark matter. This is the lifetime of the universe. I'm just putting it in this context so that you can kind of say, how if I set f equal to 1, then how long does dark matter have to live? You might think that all that you have to have is dark matter live the age of the universe and you're fine. But actually you need it to be more stable than that, because if it's decaying on timescales which are that of the universe, then its equation of state will be sufficiently different from ordinary matter that it won't look like dark matter, and you'll get your cosmology wrong. So you need dark matter to live sizably longer than the age of the universe, even if it's decaying invisibly, to be consistent with data.
May as well be infinite.
Well, I don't want to say that. There are plenty of situations where we don't expect the proton to be stable.
That's true.
And yet it is stuck around for a long time. Yeah. Makes an assumption that the decay products are relativistic. Yeah. If it's dark matter decaying into dark matter, then it's okay. This is dark matter, but this is dark matter decaying into relativistic particles. Oh, no. If it were dark matter standard model, then it would make it a much, much worse constraint. Because if it were, say, dark matter decaying to, say, photons, then you have to worry about those photons over the course of the universe showing up in your diffuse background or breaking apart nuclei. If it's decaying to electrons, then you have to look for those in AMS. Then it's a very mass dependent. But then it's a limit that you have to worry about in context of indirect detection experiments, looking for the cosmic ray signals of that decay. Yeah. Oh, this bound just comes from looking at the growth of structure in the universe and making sure the growth of structure and the CMB are all as they should be. And if you allow dark matter to decay this fast, then its properties are sufficiently different that you screw up things at levels that are inconsistent with our current cosmological data. All right. So if you want to build a model of dark matter, you just had us to satisfy these things, and you'll probably be fine. So we'll start this afternoon building such models.